Most momentum problems are won or lost before a single equation gets written. Two decisions do the work: what you put inside the system and which direction you're asking about. Get those right and the algebra is bookkeeping. Get them wrong and no amount of algebra will rescue you. So here is the method, laid out as a strategy you can run on any problem in this chapter. The strategy has 4 steps. Understand. Get a conceptual grasp of the problem. Devise a plan. Set up a procedure that will get you the solution. Carry out your plan. Solve it. Look back. Check your solution and your method. The last 2 steps are where the arithmetic lives, but the first 2 carry almost all of the physics. They are the ones we're slowing down for, so those are the 2 we will develop. Understanding starts with one question. Is momentum constant for the system that changes state? You cannot answer it until you have said what the system is. Identify the objects that make up the system, and identify how the interaction changes them. A useful guide is to look for the objects whose momentum changes during the interaction, and to draw the boundary around those. Then keep track of the momentum of everything inside, both immediately before the interaction and immediately after it. Forces from outside that reach across the boundary are the external forces, and they are what you check next. Momentum is a vector, so asking whether momentum is constant is never one question. It is one question per direction. The tool is Newton's second law for a system. The net external force equals the rate of change of the system momentum. That is a vector equation, so it holds component by component. If the external force has no component along x, then the x component of the system momentum has 0 rate of change. And in that direction, the momentum is constant. Constant, not 0. Those are different claims, and the difference is where most errors start. A system can hold its momentum fixed along one axis while its momentum changes along another in the very same problem. A projectile is the standard case. Gravity acts downward, so vertical momentum changes every instant, while horizontal momentum never budges. There is a second subtler case where external forces do act and the momentum still gets treated as constant. Recall the integral form of the law. The average external force times the interaction time equals the change in the system momentum. The size of that change is set by a product, and a product can be made small by either factor. If the interaction lasts a short enough time, the impulse is small in magnitude compared with the momentum the system already carries. The change in momentum is negligible, and you set it to 0. That is what licenses treating a collision or an explosion as momentum conserving, even while gravity acts throughout. Notice what short means here. Short is never absolute. It means short enough that the impulse the external force delivers is small compared with the momentum already in play. Now the fork in the road. If the momentum is not constant, you must apply one of the 2 impulse momentum statements. The differential form, external force equals the rate of change of system momentum, or the integral form, external impulse equals the change in system momentum. If the momentum is constant, you get the far friendlier statement. The initial system momentum equals the final system momentum. One vector equation standing in for the whole interaction. And if only one direction is free of net external force, you keep only that component. The initial x component of the system momentum equals the final x component. Answer the question direction by direction, and write down only the equations you have earned. Step 2. Devise a plan. Draw every element of your system twice. Once in the state immediately before the system changes and once immediately after. Give each mass and each velocity its own symbol. Choose a set of positive directions and unit vectors, and use the same choice in both states. Then choose symbols that match the state and the motion, because that is what makes the result readable later. The x component of the velocity of object 1 in the initial state is written as a lowercase v carrying subscripts x and I. the whole thing wrapped in parentheses, with a subscript 1 hanging outside them. In the final state, f replaces I. Decide up front whether your velocity symbols mean components, which can be negative, or magnitudes, which cannot. And because momentum is a vector, identify the initial and the final momentum components as well. These paired pictures are what we call momentum flow diagrams. With the diagram drawn, the model becomes algebra. Take a system of objects that move only along x, 2 of them here, and the pattern extends to as many as you have. The initial x component of the system momentum is mass 1 times the initial x velocity of object 1 plus mass 2 times the initial x velocity of object 2 plus however many more terms the system needs. The final x component has exactly the same shape with f in place of I everywhere. If the x component of the momentum is constant, those two expressions are equal, and substituting gives the equation you actually solve. Mass 1 times the initial x velocity of object 1 plus mass 2 times the initial x velocity of object 2 equals mass 1 times the final x velocity of object 1 plus mass 2 times the final x velocity of object 2. Every unknown the problem is hiding sits somewhere in that line. That equation carries whatever analysis the problem needs. Often it holds enough information to solve for the final velocities, and that is step 3. Carry out the plan. Then step 4, look back. Check the dimensions and the units on every line. Check the vector directions so that a negative component means what your chosen positive direction says it means, motion the other way. And check the method itself. Was that the right system? And was that direction genuinely free of external force? 2 worked examples come next, an exploding projectile and a landing plane that snags a sandbag. Neither one introduces a new principle. Both are this method, carried out. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.